Hi there and welcome to the walkthrough for the Algebraic Proof, the maths question. Just get stuck in. Again, feel free to just pause or skip to the end and just have a look at the answers if you want to just mark them off, or sit and watch if you need to know how to do anything. So with each one of these proofs, just think about what your expectation is in your outcome. So prove that something is always a negative integer, so I need to be able to write it as minus something. Okay. So we'll just crack on and just get into it. So we get 4p minus 12 minus 4p plus 2, the double negative there. So 4p minus 4p cancels, minus 12 plus 2 is negative 10. So regardless of the value of p, you're always going to get a negative number there, so you get minus 10. Okay. Prove that this is always a multiple of 5 when y is a positive integer. So again, just get into it. 8y plus 24 plus 6 minus 3y. So 8y minus 3y is 5y plus 30. And then just to finish, factorize. So we can say that 5 times anything is a multiple of 5. And the reason the positive integer part is there is because when we say multiple of 5, we normally mean positive numbers like 5, 10, 15, 20, so therefore y would have to be positive in order for that. Well, not always positive, but not a big negative number. We don't normally include negative numbers as being multiples. So a is a positive integer. Prove that this is a cube number. So again, we're just expecting to get something cubed at the end, so let's just get into it. So we'll have 4 times 2 is 8a cubed plus 4a squared minus 2a squared is 4a squared. Oh look, they cancel, which equals 8a cubed. Now just for clarity, then we're going to write that as 2a all cubed, which is a cube number. With all of these you could finish them off, I'm not here with a sentence to say, and therefore it is a cube number. Or therefore it is a multiple of 5. So a and b are positive integers, a less than b. Prove that this is less than 1 when x is not equal to negative 3. Okay, so for this one then, again, just do what you can do, see what happens. So we can factorize this. So a comes out of x plus 3, and b out of x plus 3 again. Oh, I've written b there, 3, which means you can cancel that and that. So you've got a over b. If a is less than b, this implies that a over b must be less than 1, because obviously you've got a proper fraction there. Okay. Question 5, express blah in the form blah. So it's just asking you to complete the square. So our answer on that one is just going to be, this is further maths, so I'm just going to assume that we can complete the square. X plus 3 all squared minus 9 plus 11, which obviously is x plus 3 squared plus 2, so leave that there. And then hence prove that this is always positive. Okay, so you've already got what you need, it's just, again, it's a sentence. Let's try to fit this in. So we've got x plus 3 all squared plus 2, and x plus 3 squared is always greater than 0 because it's a squared number. Again, we can write a sentence. Therefore, x plus 3 squared plus 2 is also greater than 0 because we're adding a number to it, and therefore it's always positive. Graphically, if this was like y equals, this would mean that the turning point is above the, or yeah, it's above the x-axis. Okay, so you'd have a little sneak it in, a little pitch, something like that. No solutions, and also another important point from that. So prove that for all values this is greater than 0, so it just follows on. Just do the two markers as one thing, so we'll complete the square, so we'll get x plus 1 all squared, minus 1 adds 6, so plus 5, and then I won't go through it again, but essentially you do the same thing again. You say that this is always greater than 0 because it's a squared number, plus 5 is also greater than 0, and therefore the function is always greater than 0. Okay, so a function is equal to this. Prove that there is exactly one value of x for which f of x equals 0. Okay, so to say that in another way, essentially there's just one solution to the equation blah 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 equals 0. Okay, so f of x is the function, this is the function. So if we just get stuck in and expand this bracket, we get 4x squared plus 3 times 2x, which is 6x twice, so you get 12x from that, plus 9, plus 8x, plus 2. Tidying this up, we get 4x squared plus 20x plus 11. No, we don't, because 8 times 2 is 16. There we go. So 16 and 9 is 25. Down to myself now. Is that right? 3 squared is 9, and 8 times 2 is 16. So yeah, whatever. Equals 0. So one shows that you've got one solution, so you could try and find that solution. The better way to do it, I think we spoke about it in one of the previous videos, is to use a discriminant. Okay, so if there is exactly one value, one solution, that implies that if we were to use the quadratic formula, let's have a look at the quadratic formula. That must mean that there is no plus or minus bit here, because if I add or subtract a number away from a b before dividing it by 2a, then it's going to create two different numbers, whereas if this bit here is 0, I'm adding or subtracting 0 away from minus b, so it creates the same number. So for one solution, b squared minus 4ac equals 0. So b in this instance is 20, so 20 squared minus 4 times 4 times 25. Oh, that's worked out nicely, isn't it? 4 times 20 is 100, and that's 400 equals 0. This implies only one, or repeated roots, another way to say it, one real solution for f of x equals 0. Okay, question 8. Oh, this is a quick one, isn't it? Nice. The nth term of a sequence is blah. So this tells us then that to generate any term in a sequence, that's our formula. So work out an expression for the n minus 1th term in the sequence. So I think we've seen this question before, haven't we? I think we had an extension question or something. I seem to remember James getting it right. De Villiers. Anyway, I digress. So let's do that. So for the n minus 1th term, we have a half times n minus 1 where we see n, and then n minus 1 where we see n again plus 1, because there was a plus 1 there. I realise I'm doing that pointing thing again where it doesn't show up on your screen, apologies. So we've replaced this n with n minus 1 and this n with n minus 1. So we get half times n minus 1 times minus 1 plus 1 is 0, so times n. So expanding that, we get n squared minus n over 2, although to be honest, leaving it as n minus 1 over 2 is probably simpler, potentially. Hence, or otherwise, prove that the sum of any consecutive pair of terms of the sequence is a square number. Okay, so what we've got then is this up here is the nth term, this down here is the n minus 1th term. So if I stuck in, say 3, right, into both of these, then this would give me the third term up here, and then this would give me the second term, the one before, for n is 3. So if we want our two consecutive terms, we're running out of time here, aren't we, in the second video? If we want two consecutive terms, we can use this, and we want the sum of them, so we just add the two together, and apparently this gives us a square number. Alright, so let's just see what happens. So we're going to have a half of n plus 1 for the nth term, plus n minus 1 over 2 for the n minus 1 term, add two consecutive terms, and what do we get? Well, they're both over 2 already, so we've got, if we expand the bracket actually, it'll be easier, n squared plus n over 2 plus n squared minus 1, sorry, minus n, beg your pardon, over 2. So then we'll end up with plus n minus n will cancel, so both over 2, n squared plus n squared will give you 2n squared, so we'll end up with, pop it up,